I am Mr. K.Himaja, working as a lecturer in EEE Department, SRRS, Government Polytechnic Sirisilla. Now, this Part 16 presents the Unit 4 of Electrical Estimation and Utilization. So, first one is the nature of light and its propagation. Second one is the definition of the following terms: plane and solid angles, B. Luminous flux, luminous intensity, lumen, candle power, and illumination. So these all are the part of the fourth chapter. So nature of light and its propagation. The objective, that is the first objective, and second objective is the definition of the different terms: plane and solid angles, luminous flux, luminous intensity, lumen, candle power, and finally illumination. So the illumination introduction. Study of illumination engineering is necessary not only to understand the principles of light control as applied to interior lighting design, such as domestic and factory lighting, but also to understand outdoor applications such as highway lighting and flood lighting. Here illumination means light. Nowadays, the electrically produced light is referred to the other source illumination because of an account of cleanliness, ease of control, steady light output, low cost, and reliability. The best illumination is that it produces no strain on the eyes. Apart from its aesthetic and decorative aspects, good lighting has a strictly utilitarian value in reducing the fatigue of the workers, protecting their health, increasing production, etc. So the science of illumination is engineering is therefore becoming of major importance. Nature of light. Light is a form of electromagnetic energy radiated from a body, and a human eye is capable of receiving it. So we have to, our eyes has to receive the light, means different colors, different waveforms, depends on the angstrom units, like that. Light is a prime factor in the human life as all activities of human being ultimately depends upon the light. Various forms of incandescent bodies are the sources of light, and the light emitted by such bodies depends upon their temperature. So depends on temperature, it will vary. So a hot body about 500 degrees to 800 degrees centigrade becomes a red hot, and about 2500 to 3000 degrees centigrade the body becomes white hot. Here these are the temperature variations and important for ESET exams also. 500 degrees to 800 degrees becomes a red hot. 2500 to 3000 degrees centigrade becomes white hot. While, next point, while the body is red hot, the wavelength of the radiated energy will be sufficiently large, and the energy is available in the form of heat. So means the body temperature is in 500 to 800 degrees centigrade. The wavelength is sufficiently large and it is available in the form of heat. Further, the temperature increases, the body changes from red hot to white hot state. So already in previous slide we are discussed. Red hot means 500 to 800 degrees centigrade, while white hot means 2500 to 3000 degrees centigrade, means the body temperature is rising. The body temperature is rising. So initially red hot, if the temperature increasing, it becomes white hot. So the wavelength becomes smaller in this stage and enters into the range of wavelength of light. The wavelength of the light varying from 0.004 to 0.00075 mm, that is 4000 to 7500 angstrom unit. For 1 angstrom unit means here, so 4000 to 7500 angstrom units it is varying from. So 1 angstrom unit is means 10 to 10 mm. The eye discriminates between different wavelengths in this range by the sensation of color. So here 4000 to 7500 angstrom unit. So the wavelength is varies from 4000 to 5000, 7500, in between different colors are present. Depends on wavelength. So at 4000 one color is present, 6000 one color is present, 7000 one color is present. In between 6 to 7000 one more color is present, and 4000 to 5000 one more color is present. So here the wavelength is varies from 4000 to 7500 angstrom unit. So the eye discriminates Depends on wavelength, the color varies. Next one. The whole of the energy radiated out is not useful for illumination purpose. So what is the energy output? That is light. So the light whole is not used for illumination purpose. Means some of the light, some of the illumination is wasted. Because it goes to the corners, it goes to the tops, it goes to the edges like that. The radiations of very short wavelength varying from 0.000156 into 10 power minus 6 m to 0.001 into 10 power minus 6 m are not in the visible range, are called as Rontgen or X-rays, which are having the property of penetrating through opaque bodies. Here for X-rays, the wavelength is very short, very small. That is, it varies from 0.000156 into 10 power minus 6 m to 0.001 into 10 power minus 6 m. Means we can imagine the wavelength of that corresponding one. What is the short? So the terms used in illumination, color, the energy radiation of the heated body is monochromatic, that is, the radiation of only one wavelength emits a specific color. So the wavelength of visible light lies between 4002 and 7500 angstrom unit. The color of the radiation corresponding to the wavelength as shown in figure 1. Here the wavelength varies from 4000 to 7500 angstrom units. So it is represented in the next figure, next slide figure. Figure 1, wavelength. Here the y-axis represents the sensitivity of the human eye and the x-axis present the wavelength here shows from 4000 to 7500. So you have to remember this is very important for ESET exams and also competitive exams. Definitely one question will come from this wavelength graph. So you can observe here how many colors are present, different colors are present. So depends on our sensitivity and depends on wavelength, the color will vary. So at one particular value, one color is present. So here totally the colors are violet, blue, green, yellow, orange, red and infrared. So at 4000 violet color is present. Just you see the figure. At 6000 yellow color, 6500 orange, 7000 red, 7500 infrared is present and 5000 green color is present. So in this wavelength in between, so the blue is present at 4500 to 5500. So these are the colors of the wavelength. depends on our sensitivity and depends on our wavelength, the colors will vary. Relative sensitivity is the next topic. The reaching power of the human eye to the light waves of different wavelengths varies from person to person and also varies with age. Here the sensitivity and the wavelength is not constant for all the human beings. It varies from person to person because it depends on number of factors, age, person to person, and etc. So the average relative sensitivity is shown in figure 2. So the eye is most sensitive for a wavelength of 5500 angstrom unit. The eye sensitivity is 5500 angstrom unit, important objective bit. Means in between 4000 to 7500. Means in between green and infrared. So 5500 angstrom unit, the eye sensitivity wavelength is. So that the relative sensitivity according to this wavelength is taken as unity. The relative sensitivity according to this wavelength is taken as unity. So from the figure 1, just you see this one referred from figure 1, blue and violet corresponding to short wavelengths and red to the long wavelengths means orange, yellow, green being in the orange, yellow, green being in the visible region of wavelength. So here see this one. So here now blue and violet, blue and violet, blue and violet corresponding to short wavelengths because 4000 and in between these are present, blue and violet. So name as a short wavelengths. And red, see this one red is the long wavelength. Here blue and violet are the short wavelengths. Red is the long wavelength. Orange, next one, yellow, green. So these are middle of the visible region of wavelength. So first one, violet, blue are the short wavelengths. Next one, red is the large wavelength. Green, yellow, orange are the middle wavelengths. Next one, see 5000 green and 6000 yellow. What is a human eye? Wavelength 5500 angstrom unit. 5500 angstrom unit means what is the color? It is yellowish green. Yellow, green. Because 5000 is the green, 6000 is the yellow. So the 5500 is a greenish yellow color. So this is not suitable for most of the applications since it is yellowish green. So here from this figure we can observe the y-axis shows the sensitivity, x-axis shows the wavelength, the violet is the short wavelength, red is the long wavelength, orange, yellow and green are the middle visible region of wavelength. And 5500 is the in between 5000 to 6000. So the colors are green and yellow, means the combination 5000 to 6000 greenish yellow color. So it is not suitable for most of the applications. So from this figure 1, we can observe these points. So the second point goes to the color corresponding to 5500 angstrom unit is not suitable for most of the applications since yellowish green color. Already we are covered in figure 1. The relative sensitivity at any particular wavelength is known as relative luminous factor. The relative sensitivity at any particular wavelength is known as relative luminous factor. Wavelength means represented by lambda and relative luminous factor is represented by K lambda. Figure 2. The average relative sensitivity. So the eye sensitivity is the y-axis. X is the wavelength in angstrom units. So it is varies from 4000 to 7000. And the y-axis varies from 0.2 to 1. So at 5500 is the human eye wavelength. It is in the form of yellowish green color, means 5000 to 6000, these are the vary. Next one, light. So it is defined as the radiant energy from a hot body that produces the visual sensation upon the human eye. It is expressed in lumen hours and it is analogous to watt hours. In our power systems, in our electrical engineering, it is a power, kilowatt hours, watt hours. Similarly, in the light illumination, it is the lumen hours. So, which is denoted by the symbol Q. Lumen hours is represented by the symbol Q, which is denoted by the symbol Q, watt hours, here lumen hours. Luminous flux. Luminous flux, it is defined as the energy in the form of light waves radiated per second from a luminous body. It is represented by the symbol phi and is measured in lumens. So luminous flux, the units are lumens by phi. Suppose the luminous body is an incandescent lamp. The total electrical power input to the lamp is not converted to luminous flux. Some of the power lost through conduction, convection and radiation, etc. A fraction of the remaining radiant flux is in the form of light waves, lies in between the visible range of wavelength, that is between 4,000 to 7,000 angstrom units as shown in figure 3. So, the flux diagram. So, the input to the bulb, power input. Next, the output from the bulb is the radiant flux. Next, luminous flux. Power lost as non-luminous flux because some of the flux goes to the corners. Next one, power lost by conduction, convection and etc. So here the fraction of the radiant flux remains is in the form of light waves, means after lost, because power lost as non-luminous flux, power lost by conduction and convection etc. So the remaining flux are this lumen flux. So here the range is from 4,000 to 7,000 angstrom units. So next one, radiant efficiency when an electric current is passed through a conductor, some heat is produced to I square R loss, which increases its temperature of conductor. In general, any conductor, some current is passing, some heat is generated, because that is a copper loss, I square R loss, because the conductor is made up of either copper or aluminum conductor. Definitely some loss is present. So which increases its temperature of the conductor. So next point, at low temperature conductor radiates energy in the form of heat waves, but at very high temperatures radiated energy will be in the form of light as well as heat waves. Radiant efficiency is defined as the ratio of energy radiated in the form of light produces sensation of vision to the total energy radiated out by the luminous body. So, the radiated energy is in the form of light as well as heat waves. So, from the bulb output is the light waves. So, the ratio of energy radiated in the form of light produces sensation of vision to the total energy radiated out by the luminous body. Generally, motor efficiency means motor output by motor input. Similarly, for bulb efficiency, radiant efficiency means the energy radiated in the form of light by what is the input? Total energy radiated by the body. So that is the equation for radiant efficiency. Next one, plane angle. A plane angle is the angle subtended at a point in a plane by two converging lines. So as shown in figure 4, it is figure 4. Instead of figure 4, it is typing as 6.4. I am extremely sorry. It is in figure 4. So it is denoted by the Greek letter theta. Plane angle is represented by the letter theta and is usually measured in degrees or radians. Degrees or radians. 1 radian is defined as the angle subtended by an arc of a circle whose length by an arc of a circle whose length is equal to the radius of the circle. Here first one, plane angle means subtended at a point in a plane by two converging lines. So it is denoted by the letter theta. And measured in degrees or radians. So one radian is defined as an angle subtended by an arc of circle whose length by the arc of a circle whose length is equal to the radius of the circle. So the length is equal to the radius of the circle. Now, so this figure, next slide shows the figure of this plane angle. So here, what is the definition of plane angle we are covered? Two converging lines at a point. The angle subtended at a point in a plane by two converging lines. Two converging lines. Next point, it is denoted by the Greek letter theta. So here, two converging lines denoted by the angle theta, measured in degrees or radians. Degrees or radians. So it is the, and next one, the angle subtended by an arc of a circle whose length by an arc of a circle is equal to the radius of the circle. So two converging lines, theta, the length is equal to the radius of the circle. Here arc, draw one arc. So it is the radius r. So it is the arc. So that is the plane angle. Next one, solid angle. A solid angle is an angle subtended at a point in space by the area, that is an angle enclosed in the volume formed by numerous lines lying on the surface and meeting at the point. So here before topic it is the arc and radius. Now it is the area. So radius square and instead of arc area volume. So it is next one. It is usually denoted by the symbol omega and is measured in steradian. Before plane angle measured in theta. Plane angle is theta, measured in degrees or radians. It is solid angle is represented by omega and it is measured in steradian. So figure 5 is the solid angle. So now you see this one. The angle subtended at a point in the space by an area. The angle enclosed in the volume formed by numerous lines. Here, the angle here numerous lines lying on the surface and meeting at that point. So here the solid angle omega represented by omega and units are steradian. is equal to area by radius square is the formula for solid angle. So the largest solid angle subtended at the center of the sphere. At the center of the sphere, largest solid angle is present. So the solid angle omega is equal to area of sphere by radius square. The area of the sphere is 4 pi arc square by arc square is equal to 4 pi steradian. So the solid angle is omega is equal to 4 pi steradians. 4 pi steradians. The solid angle is represented by omega. Solid angle is represented by omega and measured in steradians. Measured in steradians. So next one, the relation between plane angle and solid angle. So what is the relation is present in between plane angle and solid angle? So now let us consider a curved surface of spherical segment ABC of height h and radius of the sphere R as shown in figure 6. Sectional view of the solid angle here. Height as h and radius as R. So the surface area of the curved surface of the spherical segment is 2 pi RH. So next one, h equals to R minus R into cos theta by 2. Means take R is the common 1 minus cos theta by 2. Next BD is equal to OB minus OD. Finally, so the surface area of the segment is 2 pi RH. So the solid angle equation is area by radius square. Finally, we got 2 pi into 1 minus cos theta by 2. 2 pi into 1 minus cos theta by 2. So h equals to here take R is the common 1 minus cos theta by 2. Next, the surface area 2 pi arc square into R minus cos theta by 2. And the solid angle finally, what is the equation area by radius square? So 2 pi into 1 minus cos theta by 2. So next one. So from the equation 3, the curve shows the variation of solid angle with plane angle. So the relation between solid angle and plane angle. So now, so the relation between solid angle and plane angle, the figure 7 shows that. So the y-axis shows the solid angle omega on y-axis and the x-axis shows the plane angle. So these are the definition of the plane and solid angle. The solid angle is represented as omega and units are steradian. Next one. Next definition is a luminous intensity. So the luminous intensity in a given direction is defined as a luminous flux emitted by the source per unit solid angle. So luminous flux emitting from the source. Here what is the definition? The luminous flux emitted by the source per unit solid angle. Per unit solid angle. So here now the luminous flux emitted per unit solid angle. Here it is the source. From this source the lights, it is the source, and the light output waves. So here this is a unit solid angle. So these are the luminous flux emitted by the source per unit solid angle. So here F is the luminous flux. So these are the flux. Next one. It is denoted by the symbol I. It is denoted by the symbol I. So the luminous intensity is denoted by the symbol I and is usually measured in candela. The luminous intensity is denoted by the symbol I, intensity, and the units are candela. Let F be the luminous flux crossing a spherical segment of solid angle omega. So the intensity formula is flux per solid angle. The luminous intensity formula is flux per solid angle. So I is equal to phi by omega. Phi by omega. Phi is the flux, omega is the solid angle. Here the flux units are lumens and omega units as steradian or candela. So the luminous intensity is candela or lumens per steradian, and the standard equation is flux per solid angle. Next one, lumen. It is a unit of luminous flux. It is defined as the luminous flux emitted by a source of 1 candle power per unit solid angle in all directions. Means indirectly what are, for example, if we take the bulb, it is the source. So bulb, the output is the flux, means lumens. In our electrical term, flux. Here luminous flux, lumens, a solid angle, the area, solid angle. So by a source of 1 candle power per unit solid angle, 1 candle power per unit solid angle in all directions. In all directions. That is lumen. So lumen is equal to candle power of source into solid angle. Lumen is equal to candle power into omega. Next. So the total flux emitted by a source of 1 candle power is equal to 4 pi lumens. 4 pi lumens. Next one, candle power. Candle power Cp of a source is defined as the total luminous flux lines emitted by that source in a unit solid angle. So candle power is equal to lumens by omega. Lumen or steradian or candela. So illumination next one, illumination. Illumination is defined as a luminous flux received by the surface per unit area. It is usually denoted by the symbol E and is measured in lux or lumen. This is a very important equation. Illumination, luminous flux per area, flux per area. So next it is denoted by the letter E, denoted by the symbol E. It is denoted by the symbol E and is measured in lumens or meter square, means flux per area. So the flux per unit area is the illumination. So 1 meter square area, how many flux are covered? Means how many lumens are covered? So already here illumination is represented by the letter E is equal to flux per area. Flux means already we are covered. Intensity is equal to flux per solid angle. Intensity means intensity is candle power is equal to flux per solid angle. Solid angle is represented by omega. Intensity is equal to flux per solid angle. Solid angle means omega. So from this equation take the cross multiplication. Flux is equal to candle power into omega. Candle power into omega. So here substitute the equation. So flux is equal to candle power into omega by area. So from this equation, flux is equal to candle power into omega. Candle power into omega per area. Units as lux. So lux or meter candle. Lux or meter candle. So the illumination is represented in lux. Lux or meter candle and foot candle I will explain in the next class. So today what are the topics we are covered? Means the nature of light and its propagation and also the definition of the terms plane and solid angles, luminous flux, luminous intensity, lumen, candle power and illumination. The light means here 4000 to 7500 varies. Red hot and cold hot terms are present. Red hot means the temperature is 500 to 800 means hot body. Red hot 2500 to 3000 degrees is the white hot. So the wavelength of the light is in generally varies from 4000 to 7500 angstrom unit. So here the color also varies. Visible light of the wavelength of the different colors from 4000 to 7500 angstrom unit. So at 4000 violet color is present. At 7500 infrared and at 7000 red color is present. In between green, yellow, orange and are present. So the eye is the most sensitive for a wavelength of 5500 angstrom unit. The short wavelength is blue and violet. The long wavelength is orange, yellow and green. Red is the long wavelength and orange, yellow and green are the middle of the visible region of wavelength. So we are discussed the flux diagram, radiant efficiency, plane angle. The plane angle is represented as theta and measured in radians or degrees. The solid angle is represented by the symbol omega and is measured in steradian. So the candle power is lumens by omega. Illumination means flux per area represented in lux. So these are the topics today we are covered. Thank you for watching this video.